Covalent bonds. Covalent bonds are formed by electrostatic attraction between a shared pair of electrons and positively charged nuclei. There is a tendency for atoms to gain a valence shell with a total of 8 electrons. That is the octet rule. Definition. Again, a covalent bond is formed by the electrostatic attraction between a shared pair of electrons and the positively charged nuclei. After I've made this video presentation, I'm going to make another on ionic bonding. An ionic bond is the electrostatic attraction between oppositely charged ions. A metallic bond is the electrostatic attraction between positive metal ions and delocalized electrons. Electrostatic attraction is such a useful phrase when it comes to describing bonds. If one electron from each atom lies between both nuclei, then both nuclei are attracted to the pair. This forms a covalent bond. Carbon has 4 outer electrons. Hydrogen has 1. The carbon atom and one hydrogen atom both share 1 outer electron. That happens 4 times. 4 single covalent bonds are formed. So I see my central carbon atom in blue, with its original 4 electrons in blue, each one being used to make a shared pair of electrons with hydrogen. And if I look at any one of those pair of electrons, hydrogen, the nucleus, in red, carbon, the nucleus, in blue, the 2 electrons are drawn between the 2 nuclei. We see that they will be attracted to both. I could draw a much simplified form of this diagram a lot quicker by just showing the carbon atom central with 4 lines showing the 4 separate covalent bonds to the hydrogen atoms. Oxygen atoms. Oxygen group 16. 6 outer electrons. The oxygen atom on the left with its electrons in blue, the oxygen atom on the right with its electrons in red. Originally 6 electrons in the outer shell, both atoms need to gain 2 electrons to get that full, stable outer shell. Oxygen atoms have 6 outer electrons. The example shows a double bond, where 2 electrons from each atom are shared. At this stage, the maximum number of bonds that can form between any 2 nuclei is 3. And again, I can simplify the diagram I've drawn with electrons shown in blue and red by writing below 2 oxygen atoms with a double bond, 2 lines drawn between them. In the previous slide, the atoms are following the octet rule. They're making enough bonds so that electrons gained by sharing provide a full, stable octet of outer electrons. It's only hydrogen that forms a full shell of 2 outer electrons, as it only has an electron in the innermost shell, which holds 2 electrons. When one atom provides both electrons in the bond, a dative bond is formed, sometimes called a coordinate bond. This can happen if one atom is electron deficient, e.g. the hydrogen ion. In the diagram opposite, I've drawn the hydrogen ion in red. Hydrogen atom starting with 1 electron, 1 proton. If the electron is lost, what remains is a hydrogen ion, H+. We've got the hydrogen ion and another atom has a non-bonded pair of electrons. In this case, I've drawn nitrogen. Nitrogen group 15. 5 outer electrons gained a full, stable octet by making 3 regular covalent bonds with 3 hydrogen atoms. But with 5 outer electrons to begin with, it has a non-bonded pair of electrons left over, used here to make a dative bond with the hydrogen ion. We saw in the last slide that 2 oxygen atoms can combine by making a double bond. And we saw that each oxygen atom had non-bonded pairs of electrons left over. One of those non-bonded pairs could be used to make a dative bond. Dative bonds shown with the arrow. I could draw a more detailed diagram. Each oxygen atom, all 3 of them, have now got a full, stable outer shell of 8. The one with electrons drawn in blue is making a double bond with the one with electrons drawn in red. The one in red is also using 2 electrons to make a third bond, a dative bond. So, another example is ozone O3, where a dative bond forms between an oxygen molecule and a third oxygen atom. Moving on a little bit, in a Lewis structure, all pairs of valence electrons are shown. With my NH4+ example, all valence electrons are shown. That's a Lewis structure. With ozone, I'm not showing the non-bonded electrons in the diagram on the left. That's not a Lewis structure. But the other one, with each electron drawn out in blue, red, and green, is a Lewis structure. The octet rule is usually followed with all atoms in the molecule getting full outer shells of electrons. Some elements, like beryllium, group 2, and boron, group 13, do not have enough electrons to share, and so they form compounds that are electron deficient. So beryllium, Be, group 2, 2 outer electrons can only make 2 covalent bonds. Nowhere near getting a full, stable outer shell of 8, not following the octet rule, we would say it's electron deficient. Similarly, with boron, group 13, 3 outer electrons. 3 outer electrons mean that it can form 3 covalent bonds, as it's doing here, but again, not having a full, stable octet of outer electrons, it's electron deficient. Atoms of noble gases already have a full outer shell of electrons, and so don't need to form covalent bonds to become stable. They form covalent bonds. I will say it's very rare. They'll form them much less readily than other non-metallic elements. Ionic substances form when one atom transfers electrons to another. One atom will need to gain electrons to obtain a full outer shell and so become stable. The other atom will need to lose electrons to become stable. Metal atoms lose electrons. They tend to form ionic compounds with non-metal atoms which gain electrons. Atoms of nonmetals tend to form covalent compounds when bonded to other nonmetals. If both atoms are of the same element, then nothing can happen if both atoms need to lose electrons. And generally, that's if the elements are in groups 1, 2, or 13. If the atoms need to both gain electrons, they can react to form a covalent bond. It's the metallic elements we find in groups 1, 2, or 13. They have atoms which tend to lose electrons, and atoms of different metals can never react. Atoms of different nonmetals do react, and they do so by forming covalent bonds. 4 different elements. Electronic structure is given. Chlorine, first off, 7 outer electrons. Both chlorine atoms need to gain 1 electron to form the covalent bond. I see the covalent bond drawn in black. Each chlorine atom also has 3 pairs of non-bonded electrons shown in red. Every valence electron is shown. That's a Lewis structure. Oxygen, group 16, 6 valence electrons. 2 need to be gained to get a full, stable octet of outer electrons. Okay, so both atoms needed to gain 2 electrons, and they did this by sharing 2 pairs to form a double covalent bond. I see my 2 lines between the oxygen atoms representing 2 shared pairs of electrons representing a double bond, and each oxygen atom, having started with 6 electrons and used only 2, still has 2 pairs of electrons left over. That is a Lewis structure. Nitrogen, group 15, electronic configuration 2,5, 5 outer electrons. 3 electrons need to be gained to give a full, stable outer shell of 8. Both nitrogen atoms needed to gain 3 electrons, and they did this by forming a triple bond. Each of the bonds between the 2 nitrogen atoms is 2 shared electrons. Nitrogen atoms, starting with 5 outer electrons, have used 3 of them in making a triple bond. Both have a non-bonded pair left over. I'm showing all valence electrons. That's a Lewis structure. Sodium, group 1, electronic configuration 281. No molecule can be made, as the atoms all need to lose electrons, and there's nowhere for those outer electrons to go. In a carboxylic acid, simplified diagram drawn opposite. The bond lengths and bond strengths between the carbon atom and the 2 oxygen atoms are different. I look at the diagram. I see the carbon is making a double bond with 1 oxygen and a single bond with the other. A double bond is shorter and stronger than a single bond. Well, if a covalent bond is electrostatic attraction between a pair of electrons and 2 nuclei, when I've got 2 shared pairs of electrons in a double bond, there's more attraction. The nuclei are pulled closer together. The bond is shorter. And surely, breaking 2 bonds is going to require more energy than breaking 1. A double bond is shorter and stronger than a single bond. Single, double, and triple covalent bonds involve 1, 2, and 3 shared pairs of electrons, respectively. Saying it again, I'm emphasizing, a shorter bond is a stronger bond. That's because the electrons in the bond are closer to the nuclei of the atoms that form the bond. If atoms are held together by more than 1 bond, then they are held closer together. Carbon atoms may form 1, 2, or 3 bonds with each other. The more bonds they form, then the shorter the bonding is, and the stronger the bonds become. Bond length decreases, bond strength increases as the number of shared electrons increases. Here. Looking at the table first, there's my carbon atoms, forming first a single bond, then a double bond, then a triple bond, and we see these are very approximate, but they are approximately the actual bond lengths. Carbon to carbon single, longer than a double, longer than a triple. Bond strengths we see increasing as I move from a single to a double to a triple bond. The pattern repeated with carbon bonded to oxygen. I see the bond length of the single bond compared with the double. The double bond is shorter. The double bond is also stronger. Halogens, group 17. If I go down group 17, F, fluorine, is in the second period. Cl is in the third period. Br the fourth period. I in the fifth period. As I go down the group, the atoms are getting bigger. Atomic radius is increasing. As the size of my halogen atom increases, then the bond length increases. The nucleus of the halogen is further away from the bonding pair. And as the bond length increases, the bond strength decreases. Okay, we've seen already, but to build on it. A dative bond is a covalent bond in which both the electrons of the shared pair originate from the same atom. Dative bonds are often called coordinate bonds. More on that in a second. We've seen already NH3, nitrogen group 15, covalently bonds to 3 hydrogen atoms, and being in group 15, beginning with 5 valence electrons, it has a bonded pair left over. Boron, group 13, we've seen already, is electron deficient. A dative bond can form between the two. Nitrogen has a non-bonded pair of electrons, while boron is electron deficient. So the dative or coordinate bond forms. Transition metals often form coordinate bonds as they have vacant d orbitals, where a lone pair of electrons can be donated. When this happens, we get something called complex ions. Species donating the electron is called the ligand. And generally, when we have complex ions, we'll refer to the dative bond as a coordinate bond. 2 quick questions. First one, identify the molecule with a non-bonding pair of electrons. I've got 4 structures. The easiest way to do that, and I'll do it separately, is by looking at the periodic table, drawing the structures out. First option was CH4. Carbon I see in group 14. 4 outer electrons, 4 covalent bonds made with the 4 hydrogen atoms, no non-bonded pair. Nitrogen, group 15. 5 outer electrons, 3 regular covalent bonds made with 3 hydrogen atoms, leaving 2 electrons left over, but they are used to make a dative bond in NH4. Boron, group 3. 3 outer electrons, 3 covalent bonds formed, no lone pair of electrons. Sulfur, group 16, 6 valence electrons. Oxygen atoms always make a double bond, and the 2 oxygen atoms in SO2 are doing just that, meaning that sulfur is using 4 of its outer valence electrons in making those 2 double bonds. 2 electrons left over. Sulfur has a non-bonded pair of electrons. So, non-bonded or non-bonding pair of electrons, D, SO2. Last question. What's the order of increasing carbon-to-carbon bond lengths? 3 possibilities. Please take a moment, pause the video. I'll explain. Again, I can do this by drawing the structures. C2H4, C2H2, C2H6. C2H6 first. Carbon, group 14, 4 valence electrons, 4 bonds made. Done. All single bonds. In the question, I'm looking to compare the lengths of, let me go back, carbon-to-carbon bond lengths. C2H4. Each carbon with 2 hydrogens, meaning I must have a double bond, shorter than the single bond in C2H6. C2H2, triple bond. My triple bond is shortest, my single bond is longest. You could do this by drawing the 3 structures out. Some people would choose to do it by looking at the formulae. If the carbon atoms have less hydrogen atoms, then there must be more bonds formed between the carbon atoms. Either way, correct answer D. Shortest bond first, leading to the longest bond. That's it, that's covalent bonding. If you got anything from this video, please like and subscribe for more videos coming out. Thank you.